In order to keep things simple in class, I gave you a simplified version of the Taylor series. So in this video, which is entirely optional, I want to go over the full version and then show you why it's useful. So the full version is this, and it's basically the same as what we did in class, except we use the number c not equal to 0, and we're going to expand around x minus c. And this is used, I'll give you an example of why this is used. So this is called expanding around c. Okay. So if c is equal to 0, as we did in class, we get this simplified version. That's called a Maclaurin series. And I wanted to keep things simple in order to get the general concepts down. But here I'm going to, again, it's optional, so you're hopefully only watching this if you're interested. If you're starting to get confused, feel free just to ignore it. But in this one, I want to show you the full version and how it's useful. And notice that c equals 0 won't work for the natural log, because if I try to look at f of 0, I get log of 0. It doesn't exist. So I really can't expand. So what we're going to do is we're going to expand c equals 1 using this formula. And that's going to be in the next page, which we got here. So I want to find a Taylor series for this. I'm going to use c is equal to 1 because c equals 0 won't work. So I need to figure out what this equals. Now, to make things easy for you, what I did is I computed the derivatives. So the 0th derivative is the function log. The first derivative is 1 over x. Second derivative, minus 1 over x squared. And third derivative, this 2 is going to come up, minus 1 times minus 2, 2 factorial, x cubed. And the pattern emerges. Now, what we're going to do is we're going to note right away this one's different. And so I'm going to plug in 1, and log 1 is 0. So what that tells me is that a0 is 0, which is great. Okay. Now I look for my pattern for k is not equal to 0, so of all the other k's. So I look at that, and what's my pattern? Well, for the kth derivative, it's going to be it's going to be negative on even. So I use that. Notice I get a factorial that's 1 less than the index. So I get k minus 1 all over k factorial. Now remember, that's my ak. Oops, sorry, that's not k factorial. That's x to the k, right? Sorry, that's really stupid. I'm sorry about that. Okay, so I want to figure out what ak is. So ak is going to be the kth derivative at 1 over k factorial. Well, plug in 1 here, and I get minus 1 to the k plus 1 over 1, which I can ignore, k minus 1 factorial. So I plug that in. So again, this is my kth derivative, minus 1, k plus 1, k minus 1 factorial over k factorial, minus 1 to the k plus 1 over k. Remember, this divided by that is just k, because k factorial is k minus 1 factorial times k. Okay, so that's my ak. So here's my series for the log. The natural log of x is equal to k equals 0. ak is minus 1 k plus 1 over k factorial, x minus 1 to the k. So there's another version. And it turns out that if you test this, this is going to be valid for x in the interval 0 to 2. And I got this from a ratio, k, that's not there. That's just k. So that's my series. Okay, that's what the log is. So sorry about that. No factorial there. So that's it.